So, now we are going to forget whatever we have learned and just learn the MCMC algorithm. MCMC stands for Markov chain Monte Carlo. Monte Carlo is a term that is used for sampling based algorithms, and Markov chain you should already know, you must have studied in a probability class. In a Markov chain there is a state and then there is a probability of transitioning to the new state, which depends only on the previous state if it is a first order Markov chain, and that is what we will be studying. So, we create a chain of states and then do whatever we want to do, and we ask the question what is the stationary distribution of such a Markov chain, and all of those that theory gets relevant here. Now, I am not going to teach you all that theory. So, if you want to understand this algorithm deeply, go home, read up on Markov chain, read up on how to prove stationary distributions, check this algorithm again, understand this algorithm, and then try to prove that the stationary distribution of what I am just teaching you is going to be the posterior probability distribution of the Bayesian network, or read the book. Right. But let us learn the algorithm together, that is our goal for today. What it is going to do is that it is going to fix the observed variable. So, that is the beauty. I am never considering anything. For the first step, I have fixed all the evidence variables. Everything that is going to happen with the evidence variables set to the values that are given to us. Now, I am going to randomly generate a state. So, I am going to set values of all non-observed variables randomly, just completely randomly, do not think too much about it, does not matter. Now, I am going to perform a random walk, a Markov chain random walk through the space of complete variable assignments, through the space of complete states. And in each move, I am going to pick a variable x, and I am going to sample that variable again. So, all the n minus 1 variables will remain the same. I am going to only change one variable, and that one variable will be calculated reflipped based on probability of x equal to true given all the other variables, and set x to be true with that probability. So, I toss a coin and set x to be true, and I repeat many times, and the frequency with which any variable x is true is its posterior probability. This is the algorithm, that is it. We will spend 2 minutes, 3 minutes understanding this, but that is it. There is nothing more to this. Of course, you do not understand this yet deeply enough, but the algorithm itself should be clear by now. There is nothing more that is going on. So, again we fix all the evidence variables, we never worry about the evidence variables again. They are always set to the values that are given to us. So, probability of B given C, C is true. Neither will I pick C nor will I sample C. C will be true throughout my process. I will set all other variables randomly. So, I randomly set burglary, randomly set earthquake, randomly set alarm, randomly set newscast. That is my starting state. Now, I will pick a random variable, let us say I pick A, and I am going to sample A again given all the other variables including C equal to true. So, C will always be true in the given part, it is never going to change. So, we will always be sampling based on the evidence, but not just the evidence, all the variables. And think about why do we sample with all the variables, think about it, you will get the answer. And we sample it and we set A to be true or false with that probability and repeat. Repeat means pick another variable, let us say we pick burglary, again sample burglary true with all the other variables and then set burglary to this value and we keep going. And believe it or not, this converges to the true posterior distribution when frequencies stop changing significantly. However, because we have started from a specific start state, initially my samples will be highly biased. So, I will get rid of the initial number of 100,000 samples or order log n samples or something like this. And there are theoretical properties on how many samples it takes to get to this Markov chain getting mixed. Mixed means irrespective of which state I started from, I have now come to more or less the same distribution, the right distribution you want to get to. That is called the mixing time. It is a theoretical concept. In practice, we say we are going to get rid of the first 100,000 samples. That is called the burn in time. Burn in time is a practical measure for mixing time, which is a theoretical phenomenon. Okay. The stationary distribution means the distribution when the probabilities stop changing, right. We have reached the point where each sample will happen with the same probability. That is called the stationary distribution, and now you have to prove that the stationary distribution exists, number 1. B, you will reach it, under what conditions will you reach it, and again I am sweeping some things under the rug. And so, for example, the Markov chain needs to be non-periodic, aperiodic, and I forget, there are two properties that are needed, maybe ergodic or something. And 3, when you reach the stationary distribution, what is the distribution you are going to converge to, and you can prove that that will be the posterior distribution. So, all of you who are slightly more mathematically inclined, I really encourage you to read more about this. This is one of the most important algorithms in the 2000s era. This is called Gibbs sampling, by the way. You would see Gibbs sampling used left, right and center again and again and again. And then its extensions, something called Metropolis Hastings or importance sampling. All of these algorithms are still very important. Whenever I have to sample from some distribution, these algorithms become extremely important. So, please read more about it. Now, one thing, how about point 2 here? Calculate probability of x equal to true given all the variables. Is it easy to do this? How do I even calculate probability of x given all the other variables? Isn't that an exponential process? Can somebody see how would I compute this? Most of them are independent. What's the name? Jay. Jay says most of them are independent. Which rule is Jay using when he says most of them are independent? Markov blanket. So, given the Markov blanket, everything else is independent. Now, this is given everything including Markov blanket. So, only the variables that are in the Markov blanket are important for this particular sampling step. So, that is the beauty of this. To compute probability of x given all of the variables, I will take parents, children and other parents of children of x and not worry about anything else. Probability of x given everything is equal to probability of x given its Markov blanket, and that you can compute using the Bayes rule. Okay. So, let us quickly take an example. You can read the specific computations of Markov blanket yourself, it is not very complicated. Let us look at a simple example. So, if you smoke, you probably have heart disease. If you smoke, you probably have lung disease, and if you have heart disease, you probably have shortness of breath. If you have lung disease, you probably have shortness of breath. And let us say I give you that I smoke and I have shortness of breath. So, this is my evidence, and now I want to figure out what is the probability I have heart disease. Okay. So, now I first start by randomly sampling the other variables. So, I let us say randomly set heart disease to be true and lung disease to be true. And now I randomly pick a variable. So, let us say I randomly pick H, okay, and I then use probability of H given SGB, all the other 3 variables, and I figure out what is that probability, and then I sample. Now, heart disease, what is the Markov blanket of heart disease? All the 3. My parents smoke, my children shortness of breath, my other parents are children lung disease. So, then I will take all these 3 and I will sample H again. So, I will compute the probability and sample H. So, let us say my sample is not H. So, now my new state is SB not H G, that is my new state. I have done one step of the random walk. Now, let us say I repeat. Let us say I repeat by saying sample another variable, let us say I sample lung disease. Now, when I am sampling lung disease, I will sample it given S, B which are evidence and not H, because that is my previous state. And again let us say I sample, suppose result is G. So, my new sample is S, B not H and G, and that is my new sample, and I keep generating these samples and so on and so forth. So, in this way I generate lots of samples, and now if I have to estimate probability of x given E, I will just check in how many samples x was a specific value given the total number of samples, and that is my answer. The beauty of the Gibbs sampling algorithm is that no samples are discarded, just like likelihood weighting, but there is no problem with low weight because I am always sampling given the evidence. I am not sampling from the prior distribution, I am sampling from the posterior distribution. As you will see, the stationary distribution of Markov chain is the posterior distribution. So, I am actually sampling from the posterior distribution. It can be implemented extremely efficiently. As you can see, the algorithm was just this much. So, it is very easy to implement. You can get like 10 years ago you could have gotten 10,000 samples a second. So, extremely fast. Now, there is a problem with this algorithm, and that is very difficult to see. So, I will quickly tell you, let us say I have two variables x, y, such that y is equal to x, but x is can be true or false with probability 0.5. Okay. So, x is uniform 0.5 and y is just exactly equal to x. So, if x is true, y is true with probability 1, and if x is false, y is false with probability 1. When I do Gibbs sampling, let us say initially both of them were 0 0. So, when I sample y given x, I will remain at 0 0, and when I sample x given y, I will remain at 0 0. So, I will only generate 0 0 0 0 0 0 samples, and so what is going to happen? I will believe that marginal probability of x is 0, which is not true, it is 0.5. I can never jump from 0 0 to 1 1. If I start from 1 1, I will remain at 1 1. So, these regions, disconnected regions, are called the modes of the Bayesian network. And if Bayesian network has modes, when will I have modes? If my path is stuck, when will a path be cut? If some probability is 0 or some probability is 1. So, it can get stuck if the relationship between two variables is deterministic, and lots of algorithms have been studied to make MCMC more robust to these deterministic settings. In fact, even if I have near determinism, like probability is very low, even then you have two practical modes, like it is very difficult to jump from this mode to this mode. As long as that does not happen, MCMC is a great algorithm and works really well and super fast. Okay. There are also other algorithms which we did not cover, and if you get to Parag Singhla's or anybody's probabilistic graphical models class, you will learn about the junction tree algorithm, you will learn about belief propagation, you will learn about variational inference methods, and you will also learn about extensions of MCMC like Metropolis Hastings and importance sampling. But it is a breadth class. So, this is where we will stop the discussion on inference. In the next class, we will talk about learning Bayesian network parameters and structure, and that will be the last class on Bayesian networks. After that, we will move on to decision making in probabilistic environment.